The myth of the robust yet fragile nature of scale-free networks and empirical analysis. So let's see what's there in the scale-free networks. Okay, the floor is yours, or the online presentation is yours. Okay, thank you.
Thank you so much for the organization of this workshop. I would have loved to be there in person, but because of visa issues, I couldn't. But I'm happy to be still able to present this work online. So this is a joint work with August Bo-Romberg and Ulrich Brandes, who is my doctoral supervisor. And we look at the robust yet fragile characterization of scale-free networks, which besides their heavy-tailed degree distribution is one of the characterizations that is most commonly held about them. And we would like to do an empirical analysis to see if this characterization empirically holds. So with this, let's do a quick recap on what scale-free networks actually are. So as you can see on the left-hand side, we are depicting a visualization of a scale-free graph with 1,000 vertices and around 3,000 edges, where the size of each vertex is depicted such that it's proportional to the degree of the vertex. And there are few vertices that are much more well connected compared to most other vertices. And the existence of such vertices could be predicted by looking at also the right skewed degree distribution of this network. And many results or statements about scale-free graphs are statements that are actually stated in comparison to a baseline. Usually this baseline is the class of random graphs that have the same size, that is the same number of vertices and edges. And in this case, if we look at a random graph that has the same size, we would see something like the graph depicted on the right-hand side, where still the size of each vertex is proportional to the degree of the vertex, and we see that most vertices have more or less the same size. And this is also depicted by the Poisson degree distribution, where most degrees are highly concentrated around the average degree of 6 in this case. But here, what is visible, structurally, the biggest difference is the degree heterogeneity and degree homogeneity, but we are mostly interested in evaluating the robustness of scale-free graphs compared to this baseline. And we can look at how these two networks compare if we subject them to the removal of their vertices uniformly at random. If we do so, we would see something like this, where on the x-axis, we see the proportion of vertices that are removed, one at a time uniformly at random, and on the y-axis, we see the proportion of vertices that remain in the largest connected component. And to have a quantitative measure of robustness, we would look at the area under the curve, which captures the average fraction of vertices that remain in the largest connected component during the course of vertex removal. And as we can see, the scale-free graph in this case that we saw earlier is a tiny bit more robust compared to the size-matching random graph. But if we consider a more informed way of removing vertices, for example, a targeted attack in which vertices with the highest initial degree are removed first, we see that now the scale-free graph becomes much more fragile compared to the size-matching graph. And this observation has been characterized as the robust yet fragile property of scale-free graphs. And that means that compared to the baseline of size-matching random graphs, they are more robust against random failures, but more fragile against targeted attacks. And this characterization is mainly coined due to the experiments of Albert and co-authors, where they mostly use preferential attachment graphs and two empirical networks. But the conclusion in their seminal paper is that scale-free networks are extremely robust against random failures, which comes at the cost of being fragile to targeted attacks. And this is a property that is not visible in their exponential counterparts, as they put it. And what they mean is size matching random graphs. And this robust yet fragile characterization of the scale-free graphs, which was an abstraction, was then further generalized by a theory that is self-consistent. And this theory basically says that if we look at networks that are evolved in a biological context or are engineered, these networks would be such that they are robust against perturbations that occur frequently in their environment. Otherwise, they would have ceased to exist and we would not have observed them. But the topology that allows them to have this characterization makes them fragile to perturbations that happen less frequently, for example, targeted attacks. And this seems to make sense. And if this is true, we would expect that not only scale-free networks are robust yet fragile, but most empirical networks from biological or engineered contexts would also show this property. And while this theory seems to be self-consistent, to the best of our knowledge, it was not empirically tested on a large scale. So this is the main goal for us. And to begin, we had to compile a large collection of networks, and our criteria was that the graphs representing these networks should be simple, undirected, and unweighted, because most studies that claimed the statements that we are looking at made their claims by initially using such graphs. And we aimed to have a maximal coverage of potentially scale-free graphs. And to do this, we included all the networks that matched the structural criteria that I mentioned earlier from 3 major studies on the abundance of scale-free networks. And the sources that we used to actually collect these networks, basically the network repositories that we used, were NetLawyer, Icon, and Connect. And these are the categories of networks that we have collected: technological, social, biological, transportation, and the networks that didn't fit into any of these categories formed their own category, namely other. So one of the disadvantages that we had to deal with, a cost that we had to pay for having maximal coverage of potentially scale-free graphs, is that, as you can see, there is an imbalance in the number of networks collected for each category. For example, the technological category contains more than 75% of the networks in our collection. And within this category itself, most networks are actually representing the internet architecture at a router level. And the reason that these networks were abundant in the sources that we looked at was that the relative ease of collection, basically. Okay, so now that we have this data, we need to have a measure of evaluating to which extent networks in this data set are scale-free, to be able to evaluate whether the robust yet fragile property specifically holds or doesn't hold for scale-free graphs. And there are 2 major ways of doing this, and it's a bit controversial, but we try to use both ways of looking at this. So one way is to say that a network is scale-free if the distribution of the degrees follows a pure power law. This has the advantage that it allows for rigorous statistical tests, but on the negative side, it's not a very realistic model because it doesn't account for exponential cutoffs, noise, and other things we would expect to see empirically. And the state-of-the-art method for this way of evaluating scale-freeness is the paper of Broido and co-authors. Scale-free networks are rare. The other way of defining scale-free networks is that we would say a network is scale-free if the degree of if the probability of a randomly sampled vertex having degree d is equal to some function L of d times d to the power of minus gamma, where this L of d asymptotically converges to some constant. And as you can see, the previous definition is a special case of this more general class, which is actually equal to the class of regularly varying distributions. And the disadvantage of this way of evaluating scale fairness is that it's impossible to have statistical tests because there are basically infinitely many choices for this class of functions L of d, and it's non-parametric, this class. But it's a more elastic model, and many distributions, for example, power laws with exponential cutoffs, are captured by this definition. And the state of the art for this way of evaluating scale fairness is the paper of Voitalov and co-authors, Scale-Free Networks. Well done. So if we look at the non-empty classes of scale fairness that we had in our collection, subject to each of these methods, in the method of Broido, we have the class of weak scale-free graphs, which are basically those for which the pure power law distribution is a good fit. We have also the class of super weak scale-free graphs, where the power law distribution is preferred to 4 alternative distribution, for example, the log normal or stretched exponential, and etc. And if this preference that is evaluated based on Wong's log likelihood ratio test is not strong enough, we say that the test is inconclusive. However, if one of these 4 alternative distributions is preferred to the pure power law distribution, we conclude that the network is not scale-free. In the method of Voitalov and co-authors, as I said, we don't have a statistical test. We cannot have a falsifiable answer. But what they did is that they used 3 statistically consistent estimators of the exponent gamma. And if we look at the maximum of these estimators, namely gamma hat, the classification they proposed is as follows. If gamma hat is smaller or equal than 1, we say that the network is not power law, because in this case, we could have nodes with a linear degree, which is not possible. And otherwise, if we exclude the case of gamma hat being smaller or equal to 1, the extent to which a network is evaluated as scale-free decreases with values of gamma. For example, when gamma hat is between 1 and 3, the second moment of the degree distribution is diverging. So we have infinite variation in the degrees, and this is the highest class of scale freeness. When gamma hat is between 3 and 5, both the first moment and second moment converge to a constant, but still the degree heterogeneity is distinguishable from a network of the same size that we would observe. And if gamma hat is 5 or larger, then we say that the network is hardly power law, because in this case, the degree heterogeneity in the degree distribution is hardly differentiable from a network that has the same size. Okay. Now let's look at the results if we evaluate the networks in our collection based on both of these methods that are very different from each other. And this is what we would see. So according to the method of Broido et al., 72% of the networks in our collection are weakly scale-free. That means the pure power law distribution is a good fit. And according to the method of Voitalov et al., 83% of them have a diverging second moment. So it seems that both methods agree that most networks in our collection seem to show indications of being scale-free, But if you remember from the data collection slide, technological networks were highly overrepresented in our collection. So 75% of the networks in our collection were technological. So it makes sense to look at technological networks in our collection and whatever remains separately. And if we do that, we see that almost all of the technological networks, 92% in the case of Broido et al. And 99.7% in the case of Voitalov et al., fall in the highest class of scale freeness according to each method. And if we exclude them from our collection, then basically whatever remains lacks indication of being scale free, because then most other networks fall in these categories. So in simple terms, if we would like to see what's going on with the scale-free graphs in our collection, it's sufficient to look at technological networks, because those are the best candidates to be classified as scale-free, as agreed by these two very different methods. And whatever else is in our collection is mostly not scale-free, again, according to these both very different methods. Now, besides having a measure of evaluating scale freeness, we also need to evaluate relative robustness of the networks in our collection. And I'm going to explain with an example how we do this. So if we have an empirical network, we would generate 1,000 size matching random graphs. And then for a given vertex removal strategy, let's say targeted attacks, we compute the vertex removal orders for each of the generated random graphs, as well as for the empirical network we are looking at. And then given a graph and a vertex removal order, we can see what is the average fraction of vertices that remains in the largest connected component during the course of removing these vertices one by one. And let's call this robustness score for the empirical network X. And we would assume that the average robustness score for the generated random graphs is mu with a standard deviation of sigma. And then we can use z-scores to evaluate the relative robustness of the empirical network compared to this baseline of size matching random graphs, subject to the fixed vertex removal strategy, in this case, targeted attacks. So, for example, if we would like to evaluate whether a network is robust yet fragile, then what we would like to see is this z-score to be positive if the vertex removal strategy is random failures, but the z-score being negative if the vertex removal strategy considered is targeted attacks. Now, if we look at these z-scores for the networks in our collection, we see many interesting things going on. For example, the first noticeable observation is that for most networks, we see that the z-score against random failures and targeted attacks is negative. This means that most networks in our collection are exclusively more fragile compared to size matching random graphs, without any trade-offs going on, as we would expect from the robust yet fragile characteristic. And we also see that the social networks in our collection, as you can see here, are extremely more fragile compared to the other categories of networks. And if we look at this first inset, which basically contains most of the non-social graphs, we can see that most networks fall above the identity line, shown here by dashes. And this shows us that almost all networks in our collection are more sensitive to targeted attacks than they are to random failures because of falling above this identity line, except for one network depicted by the black arrow. And this one network is actually the Collins yeast interactome. If we want to specifically look at the robust yet fragile networks in this collection, those are depicted by these dotted black lines, the second inset. And we would see that only 12% of all the networks in our collection are robust yet fragile. And if we look at the technological category, which contains those networks in our collection that are best suited to be called scale-free, this percentage becomes 14.86, which is still a distinct minority. So what can we conclude from all of this? So the first conclusion is that, unsurprisingly, almost all networks that we had in our collection are more sensitive to targeted attacks than they are to random failures. But this is not the notion of robust yet fragility that we're looking at. The notion of robust yet fragility that we were examining is a statement that is stated compared to the baseline of random graphs. And in that sense, we see that most networks in our collection, including those best characterized as scale-free, are only more fragile compared to the baseline of size matching random graphs. And there is not really a trade-off going on. And those networks that adhere to this trade-off and could be called robust yet fragile, they constitute a distinct minority within the empirical networks that we looked at, even if we focus exclusively on those networks that are best characterized as scale-free. Lastly, I would like to invite you to have a look at our GitHub repository, where we share the code that you can use to automatically collect all the networks that we used in our study and pre-process them, and also reproduce all our results. And with this, I'd like to thank you for your attention. And if you have any questions, I'm happy to take them. Thank you.
Thank you very much. So, do we have any questions? Yes, so Bogomil.
Okay, so I would have the following question. So there are different features of networks that could affect this sensitivity to attacks, and one of them that comes to my mind is assortativity. So the question is, can this be taken into account in your analysis so that we actually in empirical networks see its assortativity? Maybe it also already could explain much of the results, and then maybe the null model should also take it into account.
It's a very good question. So we were also wondering what is the reason, or if there is any structural feature for which we can observe a trend. And we looked at assortativity, clustering coefficient, k-cores, and a lot of things, but it was really hard to observe a pattern that is consistent across the entire empirical collection. Perhaps what was the most interesting pattern that we could find was that in the social networks, which actually are the most fragile in our collection against both random failures and targeted attacks, what we could see was that they're very hierarchical. So most nodes that you would see in the k-core also remain in the k+1 core. And this feature was what distinguished them from basically all the other categories in our collection. So they were nested cores up to, for example, the 17th core, 18th core. And this feature was not really there for any other category that we looked at. But apart from this, we could not really find a trend like based on the structural characteristics that we looked at.
Okay, thank you very much. Do we have more questions? Yes, please.